Hi there, my name is Miss Townsend and I love math. Welcome to Math with Townsend. This video is for grade 12 students in data management who are studying for the first unit test on counting principles. This video is the third video in which I look at some review material on permutations and combinations. And this is the question that we're going to be answering throughout this video. So if you haven't already done so, please press pause and do this question on your own. So that you can see what you already know how to do and then watch the rest of the video to get all the solutions. So here's the first question. So part A says just simply how many permutations are possible. So we will discuss what this question's about while answering question A. So we have this word called institute and we're doing permutations, and of course a permutation is an arrangement of objects. And it just says permutation, so that means all of the objects, in other words, all of the letters will be rearranged. So let's look at what we have here. We have the word institute. So what are all of the letters? So there's an I, an N, an S, a T, another I, another T, a U, another T, and an E. So I've organized it like that just so I can see that there are some repeated letters. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9 letters, but some of them are repeated. In other words, some of them are identical to each other. So that 9 letters includes 2 I's and 3 T's. So we'll start by thinking about fundamental counting principle, which is that if I have 9 objects, like I do here, and I need to arrange those into 9 positions, I would say that I have 9 choices for the first position, 8 choices for the second, 7, 6, and so on. And we'd be multiplying these together because all of these choices have to be made one after another in order to complete one arrangement. So what that means is that what we're really doing is positioning 9 objects into 9 positions, which is normally just 9 factorial. But because I have repeated I's and repeated T's, I can't stop at 9 factorial. I've counted too many. So for example, one of the possible of all those 9 factorial arrangements was this word. So N, I, T, T, U, S, I, E, T. So that's one of the 9 factorial possibilities. But if I take this I and simply switch it with this I have the same word. And what that means is that every time the rest of the letters were located and all I did was switch one I with another, I shouldn't have counted another arrangement because it's identical. And what that means is I have to remove from my 9 factorial calculation all the ways that the 2 I's could be intermixed. So that's 2 factorial because the I's represent 2 objects and 2 positions. The same logic is true for the T's. Every time I placed the letters and then did nothing but rearrange the 3 T's amongst themselves, I didn't want to recount that as a different word because if I switch the T's around, it's the same word. So similar to what I did with the I's, I need to remove all of the ways that the T's could be interchanged amongst themselves, and those T's represent 3 objects and 3 spots, which is 3 factorial. So the total number of permutations is 9 factorial divided by 2 factorial times 3 factorial, because it's 9 objects, but there are 2 identical to each other, and another group of 3 that are identical to each other. So the math I need to do is 9 factorial divided by 2 factorial times 3 factorial. So the answer is 30,240. And that's how you deal with permutations in which some of the letters have been repeated, is you count as if they aren't, like the 9 factorial, and then you divide by certain factorials representing the number of repeated items. And that's because every time you simply switch those repeated items, you shouldn't count that as a different arrangement. So let's look at what the rest of the questions are. So how many permutations, and what I've done here is I've just organized those 9 letters So I separate by vowels and consonants. So there's my 9 letters, but remember that there are 2 I's and 3 T's. So we need it to begin with an S and end with an S. Well, that's a problem. There's only one S. So it's not possible to begin with an S and end with an S. And because it's not possible, the number of permutations is 0, because it's simply not possible for any arrangement of these 9 objects to both begin and end with an S. So that one was pretty easy. So now we look at the question that says, how many of the permutations of these 9 letters do not start with a T? So I'm going to sort of approach this in a way that feels wrong to me. And I just want you to pay attention to why it's wrong, and I think it's an important conversation. So if we're not allowed to start with a T, that means that there are 6 letters that I can start with. So I have 6 choices to make as to what letter to start with, and then I have 1, 2, 3, 4, 5, 6, 7, 8 positions left. But do I actually have 6 choices? Well, not really. I actually only have 5 choices, because I can't really consider that there are 2 I's, because it's the same permutation regardless of how many 5s. So in fact, I have 5 choices as to what to start with, and then I have 8 positions to fill. So if I start to kind of just blindly do this math, I have 8 letters to fill 8 positions. 3 of those will be the T's, because they definitely were not at the beginning. But what about the I's? Do I have 2 I's to rearrange or not? Well, it totally depends. If my first letter is an I don't have 2 I's left. But if my first letter is a U, E, N, or S, I do have 2 I's. And the math is different. So what that tells us is that if I'm going to start with 5 choices, because there are 5 letters available that are not T's, I have to break my math into cases. So let me reset this question and see what that would look like. So we are going to remind ourselves that there are 5 choices as to what goes first, but the math that comes after that depends on if I start with an I or if I start with another letter. So the other letters would be U, E, N, or S. And that's because the T's can't be at the start. So I'm no longer going to say I have 5 choices, because I want to do 2 different types of questions, and then we'll add them together to represent the total answer to this question. So if I do start with an I, so I'm going to make it start with an I, not a choice, and take an I off of my potential list. So what that means is I only have to worry about these 8 positions and the 8 letters left over. So there are 8 letters to arrange into 8 positions, but I have 3 T's. Now I don't have 2 I's, because remember, I put one of them at the beginning and I'm not allowed to rearrange it if there's an I at the beginning. So if I do start with an I, the total number of rearrangements is 8 factorial divided by 3 factorial. So 6,720. Now, let's say that I start with a U, E, N, or S instead. So let me, I'll just use the space below. So if I start with a U, E, N, or S, so 1, 2, 3, 4, 5, 6, 7, 8, 9 positions. So first of all, I have 4 choices as to what goes first. Choose between U, E, N, or S. Then I have 8 spots left over. And in those 8 spots will go, let me get back up here. In those 8 spots will go 2 I's, 2 T's, and the 3 letters that were left over. So of these 4, 1 of them goes here, and 3 of them go into the rest of the positions. So that's a total of 8 things, but 2 of them are I's, and 3 of them are T's. And don't forget, this is multiplied by 4, because that first letter could have been a U, E, N, or S. So when I do this math, 8 factorial divided by 2 factorial times 3 factorial, and then times 4, I get 13,440. So we have this many possible permutations that begin with an I, and this many permutations that begin with a U, E, N, or S, and that's all possibilities that do not start with a T. So the total number of possibilities of permutations that do not start with a T are the sum of those two different cases. So that would be 20,160. So how many permutations do not start with a T? 20,160. So I hope that is understood as to why I needed those two cases, why I couldn't just count, because those two I's, you know, it was different depending on if I started with one of the I's or didn't. Now there is entirely another way of doing this question, and it's worth looking at, and that is to use the complement method. So a complement is the exact opposite, is when you find the answer to the opposite question and subtract. So what we need in order to use the complement method, we need to remember how many total permutations there are without worrying about restrictions like this. So if we go back to question A, there were 30,240. So let me write that down, that there are a total number of permutations of 30,240. Now, in these 30,240, there are some that start with a T, and there are some that do not start with a T. And there's no third category. Either all of the words start with a T, or they do not start with a T. There's nothing I'm missing. So I'm going to count all the ways where it starts with a T, and then by subtraction, I can find the ones that do not start with a T. So again, the math I'm about to do is where I start the permutation with a T. So I know that I'm putting a T at the beginning of this word, which means there is no longer a T left to consider mathematically. This is not a choice, I'm starting with a T. So now I have 8 places left, and I have 8 characters left. So that would be 8 factorial, but there are still 2 I's to consider, and there are still 2 T's to consider. So the total number of arrangements that do start with a T is 8 factorial divided by 2 factorial times 2 factorial, which is 10,080. So of the 30,240 permutations, 10,080 start with a T, so the rest of them do not start with a T. So to find the number that do not start with a T, I'm going to do subtraction. The total number of arrangements, 30,240, minus the 10,080 that start with a T, will leave me with all of the ones that do not start with a T, which is 20,160. And again, we knew that would be the answer because it's the same answer that we got when we did it through a different method. This method may seem faster to you. It does to me. I like using the complement method. You've seen me use it a lot in class. And it means that I don't have to worrying about cases, because starting with a T is the only option here. Okay? So that's how you can approach this question 2 different ways. Let's look at part D. So in this question, we have to have the 3 T's adjacent to each other. So that means that when I consider the 9 letters, I'm going to take the T's and group them together and treat them as a single letter. And that means I now have 1, 2, 3, 4, 5, 6, 7 objects to rearrange. And those 3 T's will take up 3 spaces. So I'm also going to consider that I actually only have 7 spaces to fill, because these ones take up all that space. So I have 7 objects to fill 7 spaces, which is 7 factorial. I do, however, still have 2 I's to consider. So I have to adjust my count by dividing by 2 factorial for the I's, but I no longer have to worry about the 3 T's, because I don't have 3 T's anymore. What I have is a single letter called TTT. And there's no point in rearranging any of those T's, because TTT is the same as TTT, right? It doesn't matter how I've arranged those T's, as long as they're glued together, it's the same TTT. Hold on. that nice. Okay, so I'm not done though, because I do also have to consider that those 3 T's, oh, no, I am done. Oh, good. Because all I did was just rearrange those 7 things into 7 positions. Oh, I almost did something terrible there. So my answer is just 7 factorial divided by 2 factorial, which is 2,520. Because again, I took the things that had to be together and I treated it like a single object that was interarranged. All right, next. Now we have to have the N and the E adjacent to each other. So I'm going to do something very similar to what I did in the last question, which is I'm going to create a new letter called EN, glue it together, and treat it as a single character. So I now have, instead of 9 things, 1, 2, 3, 4, 5, 6, 7, I now have 8 things to rearrange. And because this new letter, EN, is so big, it takes up 2 positions. So I'm really only positioning these 8 things into 8 slots. So that would be 8 factorial. And then I do still have 2 I's to consider and 3 T's to consider. But unlike in the last question with the T's, EN could also be NE. And I would still have the N and the E adjacent. So what that means is that every piece of math I did for EN would be repeated if I glue them together as NE. So I'm just going to multiply this by 2 factorial to represent the fact that these glued together items could be interchanged in 2 factorial ways. And that's because there's 2 items filling 2 positions within this box. So that's how I'm going to calculate the answer. So 8 factorial divided by 3 factorial. Oops. So obviously you could type it in, all of it in, but I just said, hey, this 2 factorial will cancel this 2 factorial. So I just saved myself some time in my calculator. So the answer is 6,720 ways if the N and the E are adjacent. Next, what if the N is before the E? So we've actually seen something like this before, which is that the easiest way to think about this is if you randomly place a set of objects, half of the time the N will be before the E, and half of the time the E will be before the N. So all I have to do here is take the total number of arrangements, which you should remember from earlier was 30,240, and say that half of the time the N was before the E. So I'm just going to take the total number and divide by 2. So in 15,120 of the arrangements, the N was before the E, and in the rest, the E was before the N. And then finally, we want to contain the word sin. So I'm going to take these letters, and I'm going to create a new word called sin. So here's S-I-N, and I'm going to take that and lock it and treat it like a letter. And so up here, let me just cross those out so I know what else I have. So I also have an I, a U, an E, and T, T, T. So what I have is 1, 2, 3, 4, 5, 6. I have 7 letters, and I need to fill. Now this one here is going to take up 3 positions, so I'm actually only filling 7 positions. So these are all getting intermixed, in other words. So the answer is 7 objects into 7 positions, but I do still have 3 T's. I don't still have 2 I's because one of the I's is permanently locked in this new letter called sin, but this I is now just on its own. It doesn't have another I it couldn't switch with, and that's because I'm locking these. So the answer is just 7 factorial divided by 3 factorial, which is 840. And I think that's the last question. Yep. So just a reminder, please don't study simply by watching videos or flipping through notes you've taken. Make sure you study math by doing math. It's the only way for your brain to really register and understand it. Good luck in your studying. Thanks.